scale reading uncertainty, a digital one of plus or minus 0.1 seconds, is absolutely fine. Like if you're doing a timer in HE and you're timing how long, I don't know, a cake's been in the oven, then plus or minus 1 second would be absolutely fine, even though these guys wouldn't like it, even though it's not good enough for those guys. Bear with me, I sometimes have a slurp of tea to stop my voice getting so croaky. So, systematic uncertainties. Right, imagine we are doing this riveting experiment. We've got a bulb and we are putting voltage across the bulb with a power pack, and so we've got a little knob on the power pack. We can twiddle the knob. Start off at 0, and obviously if you're putting no volts through it, then it's not going to light at all. Then you can turn the voltage right up and make it very bright. And then we've got a light meter, and we are writing down the voltage and we're measuring the light meter's reading. So you can see the voltage 0, 1, 2, 3, 4, etc. And then we've got the light level readings here. So let's say somebody's doing this experiment and then they plot these results. So light detected by the light meter going up the way, and the voltage going across, or voltage going into the light bulb, is going up the way. And so this person plots little crosses, neat little crosses, and bangs a line of best fit through. So these points are actually these points. Do you notice anything odd about the start of the graph? What is it saying? Particularly, have a look at the 0 voltage and what that says at the light meter. Can you see at 0 voltage the light meter has a reading? Well, does that not seem a bit daft? If you're not putting any voltage across the light bulb, you know that the light bulb isn't going to light up by definition. So when the light bulb is off, so 0 volts, there is still a chunk of light being detected. So what the hell is going on? Well, in this case what is going on is that background light, in this case background light, is being picked up. So this background light is obviously going to be affecting all results, and so you can see that the expected line of best fit, or the expected relationship, which we would expect to go through 0, because if you don't put any voltage onto a light bulb, then you'd expect the light bulb not to light up at all, and well, the light bulb still wouldn't light up anymore. But if you put 0 volts into a light bulb, you'd expect the light detector not to pick up anything, but it is picking up something. So in this case it's picking up background light, and we say a systematic error, all results are affected equally. So each of the results in the experiments will be bigger, have a bigger reading, but the same amount. I don't know, they might be all 5 units bigger. So the relationship on the graph is still going to be the same. I don't know, if we think about the amount of money all of you guys in the class have in your bank accounts, and we've kind of put people in order of how much money they've got. If I then come across and I give each of you £10, well, each of you are £10 better off, but the order in terms of the amount of money people have in their bank accounts isn't going to change. So it's going to be the same relationship, but everyone's been shifted up by £10, and it's the same which has happened here. So systematic errors, all results are affected equally by something, and it's typically seen in the graph being, the expected graph being shifted around a bit. Alright, here's another example. Somebody drops a chair out of a window at school, and these are the times that it takes. So 1, 2, 3, 4, 5 readings. So the same classroom chair, we chuck it out the window from the same height, and these are the readings. So calculate the mean time. Mean just means average, so it's that plus that plus that plus that plus that divided by 5. In this case it's 1.79 seconds. You can think of the mean, or you can think of the average as like a prediction for how long a chair is likely to take. A prediction for how long a chair is likely to take if you drop it out of the window. And calculate the random uncertainty. So we do this the same as we did before. So it's the biggest, 1.81, take away the smallest, which in this case is 1.75, divided by the number. So the random uncertainty is plus or minus 0.12 seconds, which isn't bad. See, turn this absolute uncertainty into a percentage uncertainty. So an absolute uncertainty means an uncertainty which is in the same units as the figure, in this case the average figure. So we've got seconds there and seconds there, and that's called absolute. If we're going to turn this as a proportion of that into a percentage, then you do 0.012 seconds over or out of 1.79 seconds and times it by 100, and this tells us that 0.012 seconds as a proportion of 1.79 seconds is 0.7%. So that's plus or minus 0.7%. This isn't really a physicsy formula, this is sort of mathsy sort of percentages. So we've got the average or the mean, we've got the random uncertainties in absolute form, and now we've got the random uncertainties in percentage form. This now says the timer used displays 1 decimal place numbers only. State the... it's 2, isn't it? I do beg your pardon. The timer used displays 2 decimal place numbers only. 2 numbers after the decimal place only. State the scale reading uncertainty in the timer measurements. Well, it's digital, and so what we do is plus or minus 1 of the furthest digit right. So if you have a look at this again, the furthest digit right, so it's going to be plus or minus 0.0, and that's going to be 1. So the furthest digit right is 0.01. So this scale reading uncertainty is plus or minus 0.01 seconds. Turn this absolute uncertainty into a percentage uncertainty. Well, it's plus or minus 0.01 seconds as a proportion of 1.79 seconds. Turn that proportion into a percentage by timesing it by 100, and we get 0.56%. Now, what's the whole point in doing uncertainties? The whole point in doing uncertainties is to think about how we can improve the experiment, sort of like doing the evaluation of a report or the evaluation in the assignments. So there's no point in thinking you're going to improve the experiment by working on the measurement with the smallest uncertainty. You want to work on something with the biggest uncertainty. So the scale reading uncertainty in the measuring device is 0.56. The random uncertainty here is 0.7 seconds. So in this case, the random uncertainties are slightly bigger. So in this case, what we're going to do is think about experimental technique when we throw this chair out the window. Are we always making sure that the chair is held in the correct orientation as we drop it? Are we making sure that we are perfectly still when we drop it? Are we making sure we're waiting until there's no gust of wind before we drop it? That sort of thing. Right, here's another example. A student sets up a circuit measuring the voltage across and the current through a resistor. So the voltage reading, they put 10 volts through it, and because it's a digital voltmeter, this digital voltmeter is to 1 decimal place, so therefore the scale reading uncertainty in it is plus or minus 0.1 volts. The current reading, when you have 10 volts across it, the current reading is 0.50 amps, and so it's a more accurate ammeter than the voltmeter is accurate, because the ammeter gives you a figure for 2 decimal places. So therefore the scale reading uncertainty in the ammeter is plus or minus 0.01 amps. And the question asks us to calculate the resistance of the resistor, and you must include the absolute uncertainty. So, calculating the resistance, we've got voltage, we've got currents, V equals 10, I equals 0.5, R equals question mark. Well, this is just a simple V equals I, R, bang the numbers in, and the resistance comes out to be 20%. So it's a calculated value. So what's the total resistance of a calculated value? Now, the total resistance of a calculated value, we do not find it by just adding up the individual resistances. Okay? You would think maybe we do. And actually we do, and we do it at advanced higher, but the reason we do it at advanced higher is because it's not simply a case of doing that plus that. There's a statistical operation for reasons we're not going to go into. So we don't add them together, not at higher. We can get a really pretty good approximation by saying that the overall uncertainty is, to all intents and purposes, pretty much the same size as the largest individual uncertainty. the largest individual uncertainty. So what we're now thinking about is, well, which is the largest of these individual uncertainties? So we've got 10 volts plus or minus, well, the uncertainty in the voltage is plus or minus 0.1 volts, and the uncertainty in the current reading is plus or minus 0.01 amps. Now you might initially think, oh well, that's the biggest uncertainty because this number's bigger than that. But that's not really how it works, because it's all about proportions. So what is the bigger individual uncertainty? Well, you're kind of thinking is 0.1 as a proportion of 10. Bigger than 0.01 is as a proportion of 0.50. So it's not just which is the biggest number, it's which is bigger as a proportion of the number which is being displayed. And you can't really judge which of these makes up a bigger proportion, because you don't kind of have them in the same, you're not comparing them in the same units, if you like. So what we're going to do is we're going to turn each of these into a percentage of the number they're representing, and then we can compare the percentages. So 0.1 as a percentage of 10, so 0.1 divided by 10 times by 100 to turn it into a percentage, which means this is 1%, and then 0.01 as a percentage of that, 0.01 divided by 5 times 100 is 2%. So do you remember what we say to find the total uncertainty in a calculated quantity is essentially it's the same size as the biggest individual uncertainty. So this is the biggest individual uncertainty, so this is going to be 2% is going to be the uncertainty in the final calculated answer. So by using Ohm's law, we've got that the resistance of the resistor is 20 ohms, and we know the uncertainty in this is going to be 2%. Now if we're just going to write this as a percentage uncertainty, we'll say resistance is 20 ohms plus or minus 2% uncertainty. But if you think back to the question, we are asked for this as an absolute uncertainty, meaning how many ohms is 2%? So remember, absolute means we want the uncertainty to have the same units as the quantity. So we've got to say, what is 2% of 20 ohms? So 2% means 2 out of 100, so 2% of 20 ohms. This comes out to be plus or minus 0.4 ohms. So these things are the same, except this is in percentage terms. It's a percentage uncertainty, this is an absolute uncertainty. Finally, there are some parts of a higher exam which just need you to have a confident mindset of just doing it, because they're not kind of knowledge recall questions, and they're not even really process questions that you've done before. So we are thinking particularly about deliberately unfamiliar formulas, graph plotting from deliberately unfamiliar experiments, and everybody's favorite open-ended questions. Okay, you can get a sense of these by doing past paper questions on these, and I would encourage you to do some. But essentially, even if you do some past paper questions on these, because all of these are deliberately unfamiliar, then even doing past paper questions on these is not going to prepare you massively well, because the whole thing is they're going to be deliberately unfamiliar. So the best tip with these things, which people understandably hate, the best thing is just to try and build yourself up and just be confident and just flipping get stuck in. Alright? Tell yourself, bring it, and just kind of do your best and forget the rest. If you like unfamiliar formulas, they have to tell you how to use them, and there's usually, it usually looks quite complicated, but just stay with it, just be confident, read the lines of the text and it will tell you what to do with them. Graph plotting, okay? You've plotted graphs before. You know that the thing which is deliberately being changed goes on the x-axis. You know the thing which you're most interested in measuring goes on the up-axis. You know that things at the axes have got to go up in regular steps. You know that when you're plotting points, you've got to plot neat little crosses, not those bloody big horrible blobs. You know you've got to do a line of best fit, not a horrible biology dot-to-dot thing. You know when you're doing the line of best fit, it might be a straight line, it might be a